the next order of business is to remind you of the formulas that they were doing that we've been doing for from intro 1. So what are the formulas I want you to remember? Ohm's law. That's the first one. And I want you to remember power or which is also called Joule heating law. Another formula I want you to remember is V equals work done divided by charge. That brings us to the end of this section. Now, next order of business is to kind of talk to you about what is an electromotive force. Okay. So that was revision from yesterday and leftover stuff from yesterday, and this is what we're going to talk about today. What is electromotive force? Electromotive force, Griffiths has a very cool way of describing an electromotive force. We tend to think of it when we come out of intro physics as electromotive force being equivalent to the potential difference that is provided. That is only true for ideal sources of electromotive force. Basically what it is a battery that is connected to a load of some kind. It could be a light bulb, it could be, a resistor, it could be something else. So the battery provides the voltage difference, whereas the electromotive force pushes the electrons around. And in intro 1, we said that the current is the same all the way around the loop at any given moment. But the problem is, we have been discussing how electrons move. How could it be that electrons all get the same push everywhere? So that's what Griffiths talks to you about. So he says a split second after the switch is closed, the current is in fact not the same all the way around the circuit. And he then defines, and he says, what happens if there is a little kink in the wire in which the current is flowing? So there will be I in and I out. So then he says that when it reaches this point, which he calls the critical point, charges will start to accumulate. At this point. And as a result of this accumulation, there will be E fields that are developed. And these E fields will change in such a way to even out the current as the current passes through these critical points. So let me write that down. Which will then develop and these E fields will have directions such that the flow is even out. So suppose flow into the bend is greater at any instant than flow out. Charges will start accumulating. In such a way to produce an E field that opposes the current flowing into the critical point, which in turn will result in encouraging the outward flow of charge and the result both I in equal I out at all points. So it is a beautiful self-regulating system. So you can safely assume current is the same all around the circuit. And you will be absolutely correct to do that. Which brings me back to do you remember us discussing this yesterday? What's causing the push? So there are two factors in any circuit. One is called source. I think Griffith calls it FS. And the other is the electromotive What is a source? Source is any kind of battery. It could be like a chemical force that your 9-volt battery provides. It could be thermal. It could be like a battery that you've inserted into the outlet. It could be anything. So any force that is being supplied by an external force. And electrostatic force that serves to smooth out the flow. Okay, battery is only one place in the loop. Whereas the electrostatic force is responsible for the actual current flow through the loop. So the way I'm going to write this is, it communicates the influence of the source to all parts of the circuit. Do you see the difference? Battery provides the quick potential difference, but it's only one point in any loop. Electrostatic force communicates that effect to all parts of the circuit. So, in fact, I can call this push force as the sum of the source plus the electrostatic force. Okay. For an ideal source of EMF, which means, for example, a battery with resistance equals 0, internal resistance equals 0, the net force on charges, which we called F, equals 0. So that means the above equation becomes, or the electromotive force become equals to the source. And I know V equals E dot dl. Do you remember this E was the electric force that developed when we were talking here? Where'd it go? Right here. This was the E force that had developed. So may I write this here? Oh, and then there's a minus sign. I always forget this minus sign. So this becomes minus Fs, minus goes away, dot dl. And in most cases, we write that as simply V equals E. Or V equal E equal energy per charge, or energy joule per coulomb. or in fact, work done per unit charge by the source.